What are anti-photons? Do they exist? Photons are particles of light, and they are one of the fundamental building blocks of the universe. They carry energy and transmit electromagnetic forces. But did you know that there is a possible reverse to these particles? We're talking about anti-photons, a concept that has puzzled scientists for decades. Now, before we dive into the mystery of anti-photons, let's first understand the concept of antimatter. Antimatter is the equivalent of matter, but with the opposite electrical charge. When a particle collides with its antiparticle, they both annihilate each other and release pure energy. Since antiphotons are the opposites of photons, they fall under the category of antimatter. Scientists have been studying antimatter for years by observing and conducting experiments in particle accelerators. Now coming back to antiphotons, these are theoretical particles that are a complete opposite of photons, and they carry negative energy. Few scientists believe that antiphotons exist because they are inversely related to photons, and there's no research conducted so far that can support this theory. However, some argue that since photons are its counterpart in the matter world, it makes sense that antiphotons are present in the antimatter world. But as for now, the existence of antiphotons remains a mystery. Now, even though antiphotons are theoretical concepts, scientists have been striving to observe and study them to add to their understanding of antimatter. However, since they carry negative energy, it is challenging to observe them directly. One indirect method scientists use is observing the amounts of energy released when a particle and its antiparticle collide and annihilate each other. But still, it's not enough evidence to conclude the presence of antiphotons. The quest to understand the mysteries of antiphotons is still ongoing. Although there is no conclusive evidence, the potential existence of these hypothetical antiparticles could significantly impact our understanding of the universe's building blocks. It remains a lot of study and explore, but for now, the of anti-photon remains unsolved.
This is by contrast to the regular photon. We call it the dark photon. Okay, so this would be a new force carrier. So, okay, you might be thinking that's all well and good, man, but this is like a stab in the dark. Do you have any external motivation for this beyond just it might exist? I mean, a lot of things might exist. That's a good question. I like the way you think, and the answer is yes. There's a lot of motivation. I'm going to focus on just one thing, and it's because this dark actually has something to do with dark matter. So we all like to look at Hubble photographs. So take your favorite spiral galaxy, count up all the stuff you can see. That gives you the amount of luminous matter in the galaxy. Okay? Now go down, pull out your favorite textbook on gravity, and take that number and put it into the equation that tells you how fast a star should be moving as a function of how far away from the center of the galaxy it is. You'll get this prediction. Okay? Now go down to your local astronomer and get her to measure those speeds of those particles. They're totally off from the prediction. This means there has to be more stuff there than what we can see, and if it's not luminous, it's dark. That's where dark matter, this word dark matter comes from. Okay, now go down to your local astrophysicist and ask her to show you the energy budget of the universe. She'll tell you that that's the breakdown of all the stuff that exists in the universe. She'll tell you there's over 5 times as much dark matter as there is regular matter. Now go down to your local particle theorist and ask her what dark matter is. She'll tell you, we don't know. We have a lot of ideas, though. And so on the experimental end, there are a lot of people looking for dark matter directly, direct detection, not necessarily collider physicists like me, but other direct detection dark matter experiments. And, excuse me, and they have seen some weird things. And so I don't have time to go into them here, but I'm just going to tell you, you get the dark matter experimentalist into the room with a particle theorist, get them to talk together and compare notes and work it out. Eventually, the particle theorist will turn to you and she'll say, you know, if there were a low mass, if there were a new force-carrying particle that had a mass a little less than the mass of the proton, and if it interacted really, really slightly with our everyday world, this would explain a lot of the dark matter craziness that she's seeing, the dark matter experimentalist. And then as a collider physicist, you go, that's a dark photon. I might be able to create that in the collider experiment. So partially because of its relationship to dark matter, partially for other reasons I don't have time to go into, and yes, partially just because this field of dark photon searching has heated up quite a bit in the last few years. So this is the state of things as of like 2008. And that white space, completely unexplored. And that's exactly where a dark photon should live if it's going to help explain these dark matter anomalies. Now flash forward to today, just 6 years later, and this is the state of things. Those shaded regions are exclusions, places where a dark photon can't live, and the open lines are planned experiments to take place in the next few years. So what changed? Some theorists, in fact, Natalia Toro, Philip Schuster, Ruben Essig, and James Bjorken, pointed out that we can indeed look in this space for a dark photon, and we can do so on the cheap. They made some calculations, and they made the observation that we can use existing fixed target facilities that were built for other particle physics purposes to look for this dark photon. And so this is where all the experimentalists, we rub our hands together and say, yes, this is good, we can do this. And so these experiments are all over the world. They're in Russia, they're in Germany, they're in Italy, they're in California, and there are actually 3 experiments taking place that are planned to happen at a facility in Virginia called Thomas Jefferson National Accelerator Facility, or Jefferson Lab. I'm going to focus briefly on one called APEX, because that's the one that I work on. So Jefferson Lab, by contrast to the LHC, where we collide 2 beams of protons at really high energies, like tera electron volts, at Jefferson Lab, it's 1 beam of electrons that you get up to the giga electron volts, GeV scale. And then that beam of electron goes into an experimental hall, okay? And then once it goes into the experimental hall, this is what it looks like for APEX. The beam comes in over my head, it goes into this target enclosure, and then where you hold a chunk of metal fixed. So what happens when the electrons encounter the chunk of metal? I don't know, let's look at the diagram. So a chunk of metal is a dense collection of atoms with large nuclei, and so when an electron comes in, it gets close to the nucleus, they feel each other, and they exchange a photon. Okay, then as the electron bends around this nucleus, it spits off another photon, which splits into a couple of particles that we can detect. Okay, and then we detect those particles, and we calculate the mass of the particle they came from, and then we bend those up. And overwhelmingly, it's just a background noise shape, this smooth background shape. But occasionally, if a dark photon exists, you'll create a dark photon instead. But very, very rarely. And so you'd be looking, which has an actual mass. And so you're looking for a tiny bump on top of this smooth background thing. So we did this for the APEX experiment in July of 2010, where we held a test run, a proof of concept test run. And in an ideal world, we would have seen something like this. You don't have to work too hard to convince somebody that that's like a bump, but that's in fact a simulation, and what we saw was this. And if you think that doesn't look like anything, you're right. That was just a background spectrum. And in fact, the thing we'd be looking for would be a much subtler effect. It would look closer to the one on the right than the one on the left. So we did not see a dark photon, otherwise you would have heard about it, but we did rule out a small space where one can live. And we proved the feasibility of the experiment, which will happen sometime in the next couple of years, but like I said, other experiments are looking too, so this dark photon race is on. So finally, what is a dark photon? A dark photon would be a new force-carrying particle, much like the regular photon is the force-carrying particle of electromagnetism. It's dark because it interacts so slightly with our everyday electromagnetic world that it's effectively been hidden from all previous experiments, and because it could help explain some of the odd astrophysical results related to dark matter. Because it interacts so slightly with our everyday world, we need to perform specialized experiments, but at existing facilities to look for a tiny dark photon signal on top of a huge background. Excuse me. And it's potentially revolutionary because it would be the first unambiguous evidence of a fundamental particle not predicted by the wildly successful standard model that we know and love. But I mean, I know the crowd here a little bit after spending the whole day here. What would this do for you? I mean, what would you get if we found a dark photon? I mean, would you soon be able to, I don't know, take dark photos with your phone? Probably not. I mean, maybe I'm the wrong person to ask, though, because I'm an experimentalist, not a product developmentalist. I mean, I look for a dark photon because I'm interested in the fundamental open questions of physics, like what is dark matter? And more importantly, I look for a dark photon because I look at this plot and I think, I wonder what's there, much like when you're hiking, you look at a hill and think, I wonder what could be in that next hidden valley. We push the limits of human knowledge because we're curious. That being said, I do know that the simple pushing of the limits of human knowledge for curiosity's sake by my particle physics forebears has led eventually to such things as CT scans, PET scans, major advances in RF power, the World Wide Web. I have no idea what the discovery of a dark photon will mean beyond expanding our understanding of the universe. The rest of it will be up to you. So at the end of the day, though, is it possible that every single one of these experiments could come up completely empty? Yes, absolutely. I mean, these are experiments because, these are experiments, and in particle physics, there's no such thing as failure. Because even if you don't find something, you've still gained an important piece of information about nature. The only failure is to stop searching. Thank you.